Strength and reactions of acids and bases. So first thing we're going to talk about is strength. So first question you may want to ask is, are all acids dangerous? And the answer is no. You've consumed a lot of acids in your life. You had apple juice, you had lemon juice, you've had vinegar-based products. Pickles, for example, are in vinegar. Maybe you've had vinegar by itself. These are all examples of acids. And if they're all dangerous, then obviously we have problems consuming things, and we don't. So the thing that determines really if something is dangerous as far as acids or bases is basically concentration. And in particular, one chemical we're interested in for acids, if you remember, the main component that identifies acids is the production of hydronium or H+, either one. They're synonymous with each other. And for bases, hydroxide. So what we really are interested in when we're talking about is the acid or base dangerous is the amount of hydronium or hydroxide that's present in it. So strong acids have high concentrations, basically are deadly. So anything that has a lot of hydronium floating around, the reason is hydronium is a corrosive substance and it also reacts really well with your cells. So it causes a lot of damage to things around it. So it's basically a product of its reactivity, and if you have a lot of it, there's more chance for those reactions, which makes it more and more deadly. Low concentrations, still burn a little bit on occasion, maybe do a little damage, but if it's watered down, it's not going to do much because the majority of what's going to be reacting is water, not the acid. The reason is because the majority of it is water. So you may get one acid particle per 100 water particles hitting your skin, for example, and that's not going to really be deadly. So, for example, 12 molar sulfuric acid will dissolve a human body. If you've ever seen shows or heard of humans being disposed of using acids, something like Breaking Bad, which was supposed to be sulfuric acid, they called it hydrofluoric, but I think that's just to throw people off so they don't do anything silly. So for sulfuric acid, it would actually completely decompose the human body, and there'll be nothing left after an hour or two at the most. While 0.1 molar concentration of it will only create a small burn. So the concentration has a huge impact on how deadly it is. And once again, it's because of the amount of acid it's hitting you. With the 12 molar, you can get a lot of hydronium hitting your skin. With the 0.1 molar, the opposite. You get a lot of water and a little bit of acid. Are all bases dangerous? Most are used in cleaning products and tend to be safe unless you consume them. Obviously, you don't want to sit there and consume ammonia for fun, but that's an example of a base. And there's a host of others that you have in which whenever you're using for cleaning stuff. Just like with acids, it depends on the type. So concentration is a big variable in this, and the concentration for both acid and base are actually related to the solubility rules. Strong acids, like if you have a high concentration of sulfuric acid, which is H2SO4, and strong acids dissociate completely, so they break apart, so you get these hydronium ions and these sulfate ions, right? That in comparison to something like acetic acid, which is a weak acid, this is highly soluble. This breaks apart readily. It loves to break apart. Acetic acid is not. It's not insoluble, it's partially soluble, which means like for every 100 particles of acetic acid, you get one that's actually the hydronium, which would be the H+, and C2H2. I'm just associating these. Think of the H+ being synonymous with the hydronium again. So if you're only producing one of these versus, let's say you have 100 of both of these, and for this one of them breaks apart and produces hydronium. For this, all 100 break apart. So the identity of the acid is a big variable in addition to the concentration. So if you know your strong acids, you know which ones are going to dissociate readily. And if you remember the strong acids, you have H2SO4, HNO3, HCl, HBr. This is basically your Brickle. HI. Remember Brickle from your solubility rules? I put out a sequence, but it's basically Brickle. And HClO4. So these are all strong acids. So guess what that means? Everything else is weak. So if you memorize these, you've not only remembered all your strong acids, you remember all the weak acids. But once again, it's not just the identity of the acid, it's also the concentration. So if I take 1 molar of this, I'm not going to do a whole bunch of damage. It'll burn a little. If I take 12 molar of this, your hand is gone. So there's the difference right there. The concentration does play a role, but so does the identity. So what makes an acid or base strong? The amount of dissociation, which we just talked about. So the more it breaks apart, the more deadly it is. The more hydronium hydroxide. So you can see hydrochloric acid here completely dissociates, right? All these ions are broken apart. There is no HCl. For strong acids, the compound does not exist anymore. It's all dissociated. So even though it's all dissociated, because it's a low concentration, you have a very small amount of this particles compared to the water. So the majority of what's going to hit you is water when you have this hitting you anywhere. Acetic acid, on the other hand, notice just one broke apart. So even though these are the same concentration, this is going to be more deadly than this. Why? Because here, just one particle out of 100 will hit you. Here, 100 out of 100 would technically hit you, except that majority of this is made out of water. So because the majority of this is water, and this is 2, obviously, these are both majority water, it's not going to be as much damage for you. So those are 2 things you have to consider. First, identity, and second, concentration. That's how you tell if something is deadly or not. Strong acid, acid completely dissociates. So here's a reaction for that. HCl plus H2O, there's your hydronium. Instead of the H plus you've been doing so far, and there's your Cl minus. Cl minus doesn't do anything, obviously. Hydronium is what's the problem child here. So completely dissociates means that this original HCl does not exist. It's just hydronium and HCl that exists inside the solution. So here's 6 strong acids again: HCl, HNO3, H2SO4, HIHBr, and HClO4. So once you know these 6 strong acids, you basically know all the weak acids as well, because it's process elimination, right? So continuing on with this, weak acids, on the other hand, partially dissociate. So it's anything that's not one of these 6 up here. Here are your examples of, or here's an example of a weak acid reaction. This is vinegar, acetic acid plus H2O. You produce this, you produce this. Partially dissociate just means a little bit. It can be anywhere from 1 to 10 particles out of 100 dissociating. That's a very, very small number. And because of that, these are not going to be damaging to you. That's why you consume these weak acids typically. Now, if you take a 12 molar acetic acid, even though it is a weak acid, you're going to be making a lot more contact with the acid than you would with the 1 molar, right? So that can be deadly. So you've got to watch for both concentration and identity. So even if it's a weak acid, if it's a high enough concentration, it can still be harmful. So be careful with it. So this low production of hydronium is a reason that weak acids can be safe to consume, because you're only consuming 1 out of 100 particles of the acid. It's still acidic. I mean, that doesn't change, but the amount of acidity you're consuming is not that great, so it's not going to be problematic for you. All right, strength of bases. Strong bases like strong acids completely dissociate. So just dissociates completely. So that means that, and this is complete based on solubility rules. If you remember, sodium hydroxide, group 1, is always going to be soluble. So this completely dissociates, so this does not exist really in solution, just these 2 ions do. And because this completely dissociates, it's considered a strong acid, strong base. Here are your strong bases: sodium hydroxide, potassium hydroxide, lithium hydroxide, calcium, barium, sodium. These first ones, these first 5, follow the solubility rules for hydroxide, right? If you remember your solubility rules from hydroxide, the ones that are soluble are these in group 1 plus calcium and barium. We don't include the bottom ones of group 1 because they're not typical, but technically if you consider them, they would be considered strong bases as well, but they're not the strongest bases. These are. Sodium phosphate is the only weird one, because like where the heck the phosphate came from, it just, because of experimental data, is weak. All right, weak bases on the other hand, like strong bases, they have certain identification characteristics, and for this basically is that if it's not one of these strong bases, it's going to be a weak base. So by memorizing these, once again, you've memorized all your strong bases and all the weak bases, so you do 2 for 1. For this one, you can see it's following the Bronsted-Lowry approach. The H is being donated to the ammonia, which is your base. This is your acid. Here's your conjugate acid. Here's your conjugate base. So typical acid-base reaction. The only thing you need to know is that if it's not one of these bases, it's going to be a weak base. So what is a neutral solution then? When you have equal concentration of both hydronium and hydroxide. So when the concentration of the 2 is equal to each other, you are considered neutral. That typically means you have about 1 times 10 to the negative 7 moles of each of those 2 substances. Not very common, but technically it does exist, and that's how you identify them. It's basically they have equal concentration of hydronium and hydroxide. So if hydronium is higher, you're acidic. If hydroxide's bigger, you're basic. And if they're equal, you're like you are here, neutral. Distilled water is the most common example of it. So the stuff we use for experimental data collection or to do labs, that would be your distilled water. Relationship of concentration and strength, they're unrelated. Since you can have a concentrated weak acid, just like you're going to have a strong dilute acid. So they're not connected. Don't assume just because it's concentrated it's strong. Don't assume just because it's weak it's diluted. It's not the way it works. So you need both pieces of that. You need concentration and you need strength. And they're determined two different ways, right? Concentration is determined typically 6 molar and above. It's going to be your strong concentrated solution. That's your typical cutoff. 12 molar would be ridiculously high and above. But 6 molar and above, typically in a lab situation, we try to avoid concentrations higher than this because of the deadliness potential. In your labs, you typically deal with 1 molar as an FYI. Same thing with bases. Strong bases would also be about 6 molar for concentration. And then your strength is based on you memorizing your strong acids and strong bases. That's really the long and short of it. So just remember, concentration tells you how much solute you have, and strength tells you how much it dissociates. So two different things. Concentration, amount of solute. Strength, dependent on if it dissociates completely or not. So are weak acids automatically safe? One of the most dangerous acids is actually hydrofluoric acid. This is the stuff that they mentioned in Breaking Bad. A quarter size of this will basically kill you. What it does, it goes inside your system because it's inside. But the characteristic of this is really interesting because it has no net charge. It will go through your skin really easily. So if you make contact with it, this is why you read the instructions on the back of anything you're using, because the thing called industrial laundry detergent has this in it. And there's a story of somebody that actually did try to clean their clothes with that without reading the instructions. The instructions very clearly said, make sure you wear gloves. Why? If you make contact with this, it will go inside your system really well, break apart into hydrogen ions and fluoride ions, and it's a double whammy. It starts breaking down your cells at an extremely fast rate, eventually gets to your heart and kills you. If you can stop it before it gets to your heart, it'll just basically, like whatever part of your body it entered in through, that part is not going to be functional anymore. And it's extremely bad pain. So, you read the instructions, right? All right, so for this question, identify each of the following as a strong or weak acid or base. HBr, hopefully you understand it's a strong acid, because that's one of your 6 strong. This is an acid, and the reason we can recognize it is an H in the front. So is it strong or weak? Well, it's not one of the strong ones, because it's not on our memorization list. So that's weak acid. Hydroxide, that's going to be obviously a base. We know this is completely soluble, so strong base at that. Sulfuric acid, strong acid. Copper hydroxide, it's a base, right? Got the hydroxide, but it's not one of the strong ones that we memorize, so it's going to be considered a weak base. And that's how you do that particular concept. All right, we did all these already, so let's skip to the next part. So here's how you can tell. There's a chart that's usually given. They'll tell you your strong acids and bases. This is HClO4. It's one of the strong ones. So perchloric acid is strongest, and sulfuric, iodic, boric, hydrobromic, hydrochloric, and so on. So this is how you read it. Basically, the higher it is, the more acidic it is. The lower it is, the less acidic it is. And for base strength, it's the inverse relationship. So the strongest base is the one that's all the way at the bottom. For the these are conjugates, right? These are the original acids on the left. These are called your conjugate bases on the right. And the way you could kind of see what's happening here, strong acids have weak conjugates, right? Perchloric acid is a very strong acid. Its conjugate base is really weak. How do we know? It's on the top for the conjugate base part. For conjugate bases, the lower it is, the more basic it is. All right, types of acid-base reaction. Neutralization just basically means you are reacting an acid with a base and producing water and some sort of ionic compound, salt ionic compound. Keys to add enough acid to the base or vice versa so that they're equal moles of hydronium and hydroxide. That's what you're trying to do. Hydronium in a neutralization reaction, you're trying to complete, have equal amounts of it. So here's a strong base, sodium hydroxide. Here is a strong acid, hydrochloric. So we're going to try to add equal concentrations of the two because we want to neutralize this reaction. We don't want one to be bigger because whichever one's bigger is going to determine if you're acidic or basic. So for this particular scenario, Na plus and Cl react. So the way these reactions occur, they change places. It's called double replacement reaction, which you'll learn later. Long and short of it is that all you're doing for two compounds is you're trading partners. So the cations trade places. So Na goes with Cl, H goes with OH. So you get NaCl and you get H2O. So there's your salt. Is it always NaCl as the salt? No. Yeah, NaCl is salt, but other examples of salts, basically any ionic compound is considered a salt. Anything is produced from an acid-base reaction that's an ionic compound is considered a salt. So there's a whole host of them: LiCl, Na, you could go basically every combination you have it. The only thing you look for neutralization is H2O as one of the products, and you have a salt, which is basically an ionic compound. Salts are ionic compounds composed of cations and other than hydrogen, and anions other than hydroxide. So these are examples of some salts. You could see any ionic compound that doesn't involve hydrogen ions or hydroxide are considered salts. You can see some of the effects of them. Laxative, if you ever have to do some sort of stomach x-ray or CT scan, you can make you take this to kind of drain yourself out. Fun fact. Iron deficiency, if you're anemic, you'll be consuming this. And there's a whole bunch of uses for these different salts. So that's acid and bases in a nutshell.